Sure. Wonderful, everyone, and I appreciate everyone being here today. Uh, Obviously, this is our lunch and learn type of activity that we do at Create, and today we have Dr. Khalid Tantawi that is going to give us a enhancing engineering retention with fun and using the engineering box. And as you know about Create Energy, the most of us I see online, we've all done this before. So if you visit createenergy.org, you can see activities and lessons that we've done in the past. Sign up for future summer sessions that we're going to run for teacher institutes. And in fact, there we go. There's some upcoming spring webinars that are going to be happening here. So anyways, I see most of us are old hats. This video is being recorded so we can come back to it later. And I think what I do now is let me introduce you to Dr. Khalid Tantawi. He is the Associate Professor in Mechatronics at the University of Texas at Chattanooga. He has a PhD and a Master's of Science in Electrical Engineering from the University of Alabama in Huntsville, as well as a double, wow, holy cow, a double Master's in Science in Aerospace Engineering from the Institute of Superior Aeronautics and Space and the University of Pisa. He is a program evaluator for the ABAT ETAC Commission, and he previously served as a trainer for the Siemens Technic Academy. Dr. Tantawi served as the academic auditor for the Tennessee Board of Regents and is a panelist for the Tennessee Textbook Advisory Panel for the Tennessee Department of Education. He also founded the Society of Manufacturing Engineers chapter at UTC and is at Skills USA and the American Chemical Society chapters at, oh, holy cow, you were at Motlow State Community College? I didn't know that.
Seriously,
he has more than 60 journals and reference publications, and he's an active member of IEEE, the Society of Manufacturing Engineers, the Chemical Society of America, the Industrial Engineering and Operations Management Society, as well as the Tennessee Academy of Science. So at this point, I'm going to turn it over on this wonderful exercise, and I'm looking forward to hearing all of the exciting things, Khalid, and thank you for doing this for us.
Thank you so much, Chris. So let me share my screen. Okay, do you see my screen?
Yes,
yeah,
we do.
Okay, all right. Thanks everyone for joining me in this webinar. And I'll be presenting the Fun with Engineering box for enhancing student enrollment and retention. So basically here, what is the purpose of this, this box? It's obviously actually to increase enrollment and retention for engineering students. Now, there are two, I'm sure everyone actually went to recruitment activities in different high schools or middle schools or different other colleges. And what I came to realize from my experience with that is that there are two requirements when you go for recruitment. Number one, simplicity, and number two, to have something that is related to an application. In other words, an applied science. So with these two, we can recruit students because there's a significant population of students that we can recruit that are underrepresented in engineering. So for example, let's look at the current challenges for engineering. Number one, the dropout rate in engineering and engineering technology is actually nationwide, according to the ASME, is 50%. So in other words, we have 50% of the students that enroll, they either change majors or they drop out. And the majority of them, half of them, drop out within the first year. So when they are freshmen. So if you can tackle that year in the first year, and they are basically in the high school or in the freshman year, then you can reach out to 25% of the total enrollment. That is half of the dropouts, the 50% dropout. Now, the second thing is that let's look at, for example, the underrepresented populations. For instance, African Americans make up about 12% of the population, but they only make up 4% of the workforce, of the engineering workforce. Hispanics make up about 16%, but they only make up 10% or 10.9% of the engineering workforce. And the same thing for Native Americans, 1% and 0.35%. So there's also a big population that we can recruit from. The third thing is that women make up 50%, of course, of the population, but they only make up to 22% of the engineering workforce, according to the National Science Foundation. So in other words, the majority of the population actually can be recruited, and they are underrepresented in engineering. Of course, there are several factors for that, but I mean, I will go over them quickly. Like, for example, math and anxiety, according to several sources, and I have put the references in the back. This basically contributes to, is a major contributor to having this large dropout of students from engineering. And it's actually, generally speaking, female students are more susceptible to math and anxiety than male students. And the reason for that, there's several reasons, but one of the major reasons is that the educational delivery system has been developed for thousands of years to focus on or is optimized for male students, for the young boys. And as a result, it's not optimized for the female students. There's also the historical influence of family. For example, engineering has been historically labeled as a male profession. So because of this, it's difficult to remove this idea from the minds of the kids. Now, other reasons also the lower access to qualified staff at schools in minority-dominated areas, and also there are other reasons. So how can we address these issues? Basically, one good approach is called the systems approach. So using the systems approach, basically, you, rather than start with the theory from year one and year two, and the students only see theory, that's which basically causes them to drop out. You just simply start with the application. You tell them, why are they studying this theory? And this actually, you can apply it just from young ages, just by using very simple applications. And in 1 hour or 45 minutes, you can basically run several experiments that can make students understand the principles of different things in engineering, like, for example, electromagnetism. So in this box, which I actually have the parts here next to me, I put actually several, let's say, applications in simple circuits. And one of the main conditions that I looked for is simplicity. The simplest possible circuits, so that students in high schools or in first year college can build them and understand the principles. One of the major things actually that attract students, especially in the high schools and the middle schools, is, for example, solar power. Solar power is really like it's the winning application for this. There's also, for example, anything that includes dynamic things, like, for example, a motor, anything that moves, that has kinetic energy in it. Like, for example, a motor that's activated by shining light on it. And I'll show you the circuits now. There's also a whole set of experiments for electromagnetism. Now, when I went to school, electromagnetism was one of the most, it actually was probably the most difficult. It's a very difficult subject for students. It's basically all theory. And here, I looked for experiments that can demonstrate the theory very, very easily. So I'll present these briefly today. Now, let me show you the contents in a video, and I'll explain them and go over them briefly. So one of the first things actually that I mean, I continuously improve it and introduce things like, for example, here, if you want to explain, for example, the principles of electromagnetism, basically you have copper and plastic. So copper, if you have a magnet, for example, if you throw it in the copper, basically what happens, it's a magnetic field will be developed because an electric current is developed, and it slows down the magnet. But if you drop it in, for example, the plastic pipe, it will just free fall, and there's like a different, you're gonna notice there's a noticeable difference in speed. So this basically explains the principle of electromagnetism. Now, these here that you see, this is the transmitter called the Marconi transmitter. It's a very simple transmitter, wireless transmitter. This is a very simple receiver. I call this the world's simplest wireless transmitter receiver. And here, this is to explain polarization. And there's different ways to explain it, but it's basically yeah, we're gonna go over it. And this here is the light-controlled fan. As you see here, it's a fan or DC motor. And when you shine the light on this sensor here, as you see, the fan turns on. So these are, and basically along with the solar experiments are the ones that attract the most for middle school and high school students. Now here, this is the wireless transmitter receiver. As you see, it's called polarization. So they have antennas. If you notice the antennas here, both antennas are horizontally polarized, and there's a light here. There's an LED light over here that turns on whenever. So for example, when you place this in between, it will block it, but when you place it vertically polarized, it will not. Now, if we can actually merge these together. So for example, if I take the receiver here in this case, if I take the light here and connect it to this light sensor here, so this is the LED. Now I put it in so that it's right in front of the light sensor here. Now what happens? Once you turn on the transmitter, it's going to transmit the signal here and the fan will turn on. And if you use, for example, the wire blocker, it will block the signal and the fan will turn off. So this is basically, let's say, the core experiment. So, and all of these are very simple. To build them, it will take you, like in 45 minutes, you can actually build these and explain them within 45 minutes for, let's say, a senior high school or first year student. And now let me just go to the next slide. Now, along with like I said, the winning one for middle school and high school and let's say younger high schools is the solar power. So these basically, I got these from Horizon Educational. And this is basically a solar panel with a motor with a fan. So these are really good because when you start a session, for example, the recruitment session, when we go to high school, I give the students these, and immediately once they exit the building, the fan starts spinning full speed, and this gets them engaged in the session. And then after that, I show them the light-controlled DC motor, and that makes them that blows their minds. And then we have the rest of the circuits. So let me talk about the light control DC motor. As you see, it's a very simple circuit, and this circuit can be used for example, for automatic night light. You just basically switch these two here, the light dependent resistor, the sensor, and the resistor here, and it becomes an automatic night light or an automatic night DC motor. And here, basically, this is the LDR that you basically shine a light on it using just any, any light that you a source of light. And this is actually this is really one of the main things that kids love to play with. It's a very simple circuit, as you see, just a transistor, a motor, and the two and LDR and the resistor. And here we have what I call the world's simplest wireless transmitter receiver. And it's very important to make it very simple because otherwise you're just gonna overwhelm the students, and they're just gonna they'll just say, and I have had experience with that, they will just simply say, well, it's not for me. So to avoid that, I make sure the condition is that it must be very simple. And this here actually consists, and the good thing about this, by the way, is that you can connect to it any sensor, and it becomes basically whatever you like. Like for example, if I connect, for instance, a inductive sensor through a transistor to this, it becomes a metal detector, a wireless metal detector, like the students are using here in this picture. As you see, there's an inductive sensor that's connected to it, and they are basically testing different objects, to see if it catches the signal or not. Now this actually transmits the signal to a PLC that's sitting here, and the PLC makes it turns on a lamp and makes a noise, turns on a horn, or whenever they detect a metal. Now this circuit is also extremely simple. It basically consists of only a relay, so just a relay. That's all. And this is called the Marconi transmitter. Basically, when you connect a relay, the coil of the relay to the normally closed contact of the relay in series, what's going to happen? The contact is going to turn on and off. It will resonate basically, and as a byproduct, it will emit electromagnetic waves. And one of the waves is at 1 GHz. So you need an antenna. Basically, it's called a dipole antenna that is 15 centimeters, about 7.5 centimeters, or about 2 or 3 inches long on each side. And you have, that's it. You have now a transmitter. Then if you connect to it, for example, here, like I said, a sensor through a transistor, you will have, you can use any application you like. For example, like I said, you can use a metal detector if you have an inductive sensor. But this basically, if you want to do this, I would recommend that for college or senior high school only. Otherwise, you can just bring it prepared like I do for the middle schoolers and the 9th and 10th graders and lower. So here, now that was a transmitter. The receiver is also like the simplest you can find anywhere on the web. So this consists only of 3 transistors. As you see, 3 transistors. Those who know what's a transistor, they are just cascaded 3. And here we have a diode called the high switching speed diode. And I put the numbers here in case anyone wants to build that. Actually, any transistor will work, any NPN transistor will work, but here you will need high speed diodes, and that's it. Here you can put any load. Like for example, I put a buzzer, but here in this case, you can put, for example, an LED light. Of course, an LED light will need a resistor to limit the current, and voila, that's the receiver. Now the distance, they can transmit signals up to like a few feet, maybe 6 or 7 feet, or even longer, a little longer, depending on how you connect it. So this basically, like I said, you can use it for numerous applications. You can connect to that transmitter any sensor and transmit signals. Now we can go over some theory, like for example, the wavelength. I will show them like the wavelength in relation to the antenna length, or I mean like a different basic theory to explain what's going on. This is basically more in-depth theory, how how the electromagnetic waves propagate. I can actually show you these here. So this is basically the transmitter. I don't know if you can hear when I turn it on. This is the relay. The relay is now basically resonating, and it's transmitting waves. And here we have, this is the receiver. I don't know if you can see the light. The light is
Yeah,
so
we can see it. Well, kind of. It depends on how
yeah,
you hold it.
yeah. Yeah, it's
Yep.
yeah. So anyway, yeah. So if you, for example, polarize them in this way, like this, that is both horizontally polarized, they will see each other. But if you actually flip them like this, they will not be able to see each other, because one of them is vertically, the other is horizontally polarized. So this is basically polarization. That brings us to another experiment, which is polarization. And basically, like I said, so if they are both polarized in the same direction, they will see each other. If you put, for example, a mesh in between that is polarized in the same direction, it will block the electrical field. So it will block the electromagnetic wave, and therefore they will see each other. If you polarize this in the vertical direction like this, the electrical field can propagate through, and so they will still be able to see each other. I would actually, like you saw in the video previously. Now this is related to, of course, 3D movies. So 3D movies, basically, when you put on the glasses, one lens is vertically polarized and the other lens is horizontally polarized. Now they project the image from two different projectors. One projector is for example, horizontally polarized, and one projector is vertically polarized. So this horizontally polarized will be able to pass through this lens. The one that is vertically polarized will be able to pass through this lens, and that's how they create the depth. So basically, it's like tricking the eyes. One eye sees one image, the other cannot see it, and that's how you see the depth in 3D movies. And you can demonstrate that in the using these simple circuits. So like I said here, so when you put, for example, when you horizontally polarize these two, you insert this in between that is in a vertical direction, they will be able to see each other. But when you put it like this in the horizontal direction, it will not allow the electrical field to pass through, so this will not see anything. So this is basically how 3D movies work. Now, you can also, like I said, there are numerous applications that you can use it for. For example, here we have the wireless metal detector circuit that I showed you before. If you connect an inductive sensor through a transistor to the transmitter, now you can transmit. And then here, actually, I have to basically use a PLC, a programmable logic controller, and basically it does anything you like. Like, for example, here, I made it turn on a light and turn on a buzzer, and it's connected to the receiver. And another application you can use is like this, a radar. Like, for example, you read the transmitter and the receiver, and where there's something nearby, it will detect the metal, and this will turn on a light or a buzzer, for example. I'll show you, for example, here. This is going to be this final slide. So she's basically testing a metal. I don't know if you can hear the beep and the light. So here, for example, the wax doesn't turn on, but the metal part turns on the beep. And yeah, so this is basically an application. And let me just turn it off. And these are the references. Thanks so much. I think there are questions. I noticed there are questions in the chat.
I've got a question for you, Khalid, if you don't mind.
Yeah. Yeah.
Well, the first one, just a comment. I wish we would have done these kinds of experiments in my high school electronics class. That would have been fantastic.
Thanks.
But my question for you is, I'm just curious to know what age groups you've used the kit with, and what kinds of classes or student groups you've exposed with this tech.
Yeah. So actually, we used mainly for high schools, middle schools, even primary schools. I can't remember, actually, probably primary schools, high primary schools, and of course college. So college students, but it's mainly really for, I mean, the most attention you receive are from the high schools. So if it's basically, but the middle schools, basically, I actually just prepare them. I just prepare everything for the students and show them the different things. Just ask them like simple, very simple questions, like what is engineering, what is mechatronics, electricity, things like that. But if it was like high schools, the same thing, like 9th and 10th grades, maybe a little higher. If it was a 12th grade, I actually I let them actually build the circuits. I don't know if you can see here. Let me just try to, like, because of the background, I remove the background. Anyway, like, so basically I guide them. I give them breadboards. The breadboard is actually the most difficult part for them. They just cannot. It's difficult for them to comprehend how make connections on the breadboard. So I have to like guide them with draw for them what to do. But I mean, that also depends on how much time you have. So like 1 hour will be sufficient to build these. And like I said, they are the simplest you can find online. Like the transmitter and the receiver, the receiver just 3 transistors with a diode, and the transmitter just the relay. That's it. I couldn't find that simpler than that. And the good thing is that you can do all these 4 experiments: the solar, the panel with the light, the DC, the light control DC motor, the transmitter, and the wireless transmitter receiver within 1 hour.
Do you find that the high school students have some knowledge of like what a transistor is and how it works these days? I don't know that that would have been covered when I was in high school,
No,
or
no,
it's
actually,
just
no,
kind of
no,
a
they don't.
black box for them.
It's just a black box for them. Yeah,
Yeah.
no, they don't. The high schools don't know. But I mean, but like I mean, well, electricity. Some of them have good knowledge of electricity. But I mean, like typically, no, no transistor. They don't know. It's just for them a black box.
Yeah.
A lot of
But they
times, actually, I
understand
just
circuits, I would imagine, from like physical science and stuff like
yeah,
that.
yeah. Actually, a lot of times, I actually just bring one receiver with me. I just bring the receiver. I just make them build the transmitter.
Hmm.
Uh, uh, but the most one that catches their attention, that's what I start with. I actually just started with that actually this semester actually. It's the solar panel with the motor. I just it's just two connections you make, and I tell them, "Okay, let's go outside." The moment they go outside, it starts spinning, you know, and that really gets them engaged right away.
Hey, Khalid, this is Chris. I have two specific questions. The first is I could not see what brand of PLC that you used. And
I
the
think it's an
reason I'm
Ethan
asking
ones.
that is we are
Yeah.
currently doing exactly this, where we want to embed some of the electronics into our mechatronics for the typical high school students that will be coming to us and the new students that are in our current program. What kind of how do you interface to that PLC? I guess what I'm specifically asking for is the PLC code already written, that the input is already there, but they just
Oh yeah,
wire
yeah,
it
of course, of
up
course.
and
Yeah.
just kind of talk us through that because I'm actually dealing with that right at the moment.
Yeah, so this was actually a student project. I mean, this is not something. I mean, it was a student project, but I sometimes like I would take it with me. No, the PLC here, it's the micro PLC. It's by Eaton. This PLC here, but actually have used also the Siemens logo. I probably I don't have it right now with me, but the Siemens logo. It's the small. It has like four inputs, six outputs. PLC. It costs about like $100 to $150. You can get it, and it's really robust and can be programmed. And you don't need actually a software. You can just you see this screen here, a small screen. This actually can program it directly on the screen. And that's really the reason why I bring it, because you don't need to deal with any software. Just open it and you put the program in it. So that's the good thing. But this here that you see, this PLC, it comes actually from a trainer, I think by Lab Volt. It was already, I mean, it's set up. There's a trainer already that came with all this, you know, here, which I mean was simpler. I mean, you can just do the connections quickly. But I mean, like we did build things like these with a smaller PLC, with the micro PLCs. You know, different circuits. You know, but in this case, in this special case here, we used actually directly this from the trainer, the Lab Volt trainer. Now, how to interface with this? It's actually so. What I did actually, the signal that was received, use it actually. I connected to a MOSFET transistor, and the MOSFET transistor sends the signal into the PLC. The PLC, by the way, actually works on. It can work on voltages from around like uh, from around 9 volts to 24 volts. They all will send the signal for you. So in other words, like it doesn't have to be 24 volts. You can just connect to 12 volts, it will be sufficient. The same thing for the sensors here. The sensor, 12-volt sensor will work fine with 9-volt battery.
That's awesome. And we're getting into the same thing. You couldn't have hit a more timely topic for us individually here at our school and getting into it. Well, we're very quickly approaching the end of our half hour. Are there any other questions for Khalid before we sign off for our half hour activity of this wonderful Friday?
Thanks, sir. Also, I mean, I have put also here the components, like if you need, you know, I put them here on the circuit diagrams. So for example, here, like for instance, if you wanna like ever try this, you know, you can just get these transistors. Actually, any transistor will work. I tested it with the 2903, whatever it's 2903, or with these, you know, and which but the critical point, for example, here is to get the high speed. It must be high speed. A regular diode will not work. It has to be this particular diode or something high speed. For this, it has to be 12 volts. 12 volt, actually any relay will work, but 12 volt relays or 9 volt relays will be the best. Yeah, and voila.
That's great. And there's such a market for an untapped potential of students for getting into this area. So this was excellent. Well,
you so much.
thank you,
Thanks.
everyone. And Khalid, thank you so much. Wow, what an incredible presentation. And that will conclude our exercise and activity for the half hour on this wonderful Friday. Everyone have a wonderful weekend, and thank you again for participating.
Thank you so much, Chris. Thanks to everyone.
Thanks,
Have a good day.
Khalid. Great to see you. Have a good weekend.
Thanks, you too. Thanks.
Thanks,
Thanks for the
everyone.
presentation.
Thanks.